All right, so welcome to the Matroid Union Graphs and Matroid seminar. Today, I'm excited to announce that Kazuhiro is talking about IT-free and triangle-free binary matroids.
I can start?
Yeah, go
Okay,
on.
right, okay. Thanks for the invitation, Rose. So today I'll be talking about IT-free and triangle-free binary matroids. Ooh, it is working. Okay, right. So before I do so, I do want to say a bit about induced subgraphs because that's where it all starts. So everyone knows the definition. So what is an induced subgraph? So if you're given a graph G on a vertex set V, then I simply specify a set of vertices, a subset of the vertex set V, and that determines the induced subgraph. You take all the edges whose endpoints are both contained in this vertex set V. So that's what an induced subgraph is. Given a graph H, a different graph G is H3 if no induced subgraph of G is isomorphic to this graph H. So I just want to mention one very famous problem by Jefferson and Sumner that I'm sure everyone has seen. And it says that if you pick any tree T and any clique K, then you can find this constant C, which bounds the chromatic number of all these matroids, not matroids, graphs, not containing T or K as induced subgraphs. So this is a very famous conjecture, which is very much open. So I want to do something similar with matroids. So to make my life a little easier, I'll just talk about simple binary matroid. So that's the only object I'm dealing with. And for the rest of the talk, when I say matroid, I mean simple binary matroid. And it's going to be a pair, E and G, where G is just a finite dimensional binary projected geometry. And E is the ground set, is just some subset of this projected geometry G. E is going to be the ground set, and the dimension of M is going to be the dimension of G, the ambient space, if you will. When I think about matroid, I'm basically thinking of vectors, very concretely as vectors living inside F2 to the N. So if you look at this definition, then you probably notice that it's okay for E not to span G. So in the most extreme case, E can be the empty set. So that's fine in this definition. And if G happens to span G, then I'm going to say the matroid M is full rank. So since I've, in this slightly non-traditional definition of simple binary matroids, I have this explicit ambient space, I can define what an induced submatroid is by simply picking a subgeometry or flat or subspace, depending on how you see it, of this ambient space G. So I take a flat F and I take the intersection of F and E. And that determines your induced submatroid. And I'm going to write M restrict F for this induced matroid. Just basically copying what I wrote on the previous slide, I'm going to say that a matroid, so in this case, a matroid is going to be N3, where N is a different matroid, or M omits N, if M doesn't contain N as an induced matroid. So it's just a straightforward reinterpretation of the definition I wrote a minute ago. So what I want to do first is try to change alpha Sumner into a matroidal version. So let me try to do that. So the first ingredient is trees. So in the conjecture, you have trees and cliques. So for trees, I'm going to use the following matroid, which I'm going to denote by IN for a positive integer n. And it's just going to be a matroid, an n-dimensional projective geometry as your ambient space. And your ground set, in this case, I write B because I'm simply going to pick a basis. So that's going to be my candidate for trees. And I have a few examples. So when n is 1, so you're inside a one-dimensional projective geometry, which is a single element ground set. It's a very simple matroid. When n is 2, you have a two-dimensional projective geometry as your ambient space, and you've got 2 elements in your ground set. And things get a little more interesting when n is 3. So when n is 3, I3 is going to be called a claw as well. But it's a funnel as your ambient space, and you have 3 linearly independent vectors, basically. So those are my candidates for trees. And the reason, okay, so when n is 3, I3 is a claw. And the reason is that they have the property that they are maximal with respect to having no circuits. So if you introduce any additional point into these matroids, then that will create a dependency. So they're like trees in that regard. So I'm going to use them as trees. And the second ingredient in the conjecture is cliques. For cliques, we have something easier. So I'm simply going to use projective geometries as my candidate for cliques, right? Because they're the densest things you can find of any given dimension. And for two-dimensional geometries, I'm going to use the term triangle. So a triangle is just a two-dimensional projective geometry, PG12. It's in the title, so I'll be talking about triangle-free matroids a lot later. Okay, so the if I try to write down a geometric version of this conjecture, I need to have a notion of chromatic number for graphs. And the parameter I'm going to pick is the critical number, also known as critical exponent. And it's going to be defined by the following. So if n is the dimension of your matroid, which is the ambient space, then what I want to do is find a flat f as large as possible, a flat f which avoids all elements E. So here's a picture. So what I'm doing is that this blue blob is this flat I'm trying to find, and the larger the better. When I found this really large flat, which avoids all these points, so these dots correspond to points in my matroid, I'm simply going to take n minus k, where k is the size of this blue blob. So if k is large, meaning that this blob is huge, then chi will be small. In the most extreme case, if you're starting with a projected geometry as your matroid, then k is going to be 0. So the critical number is going to be k. And one of the reasons why people consider this a geometric analog of the chromatic number is that if you start with a graph G, so below the diagram, G means a graph, not the ambient space of matroids. But if you start with a graph G, then consider the graphic matroid of that graph G, then the chi of this new graphic matroid is the log of the chromatic number of the graph you started with. There are other things you can prove which sort of indicate that this is a good analog of chromatic number, but this is one of the reasons. So I'm simply going to just translate every single component of Java Sumner into these things I just described. For trees, I'm going to put these induced IS restrictions, and for keys, I'm going to put projective geometries, and chi, chromatic number, is going to change to critical number. So there's a question by Bonamy, Kadush, Kelly, Nelson, Postel from 2018, which asks, well, if you replace all these, all these components of the conjecture, what happens, right? So can you find some constant k so that if you don't have an induced IS restriction, so you don't have an induced tree or a projected geometry of dimension t, so you don't have a clique, then chi is bounded by k. So that's one question they asked, but they realized that it's not true at all, even when S and T are 3. So that's the case when you're excluding claws and Thanos as induced submetroids. So it's not, so it doesn't really feel like a complicated case, but it fails even in this case. And they found this class of matroids, which they refer to as the even plane matroids, and they have unbounded chi. So that's bad news. And if you're interested, these matroids are all have the property that if you take a 3-dimensional induced restriction, then you get an even number of elements in that induced restriction. Okay, so that's not good news. So I'm just going to draw a table, and all these cells will be filled we fill them with a number if the answer to Java sum at the metroid version is true, and the number indicates the bound on the critical number. So the first row is highly trivial because when S is 1, you can't have an induced I1, which means that you can't have anything in your ground set. So your matroid is basically empty. So that's a highly trivial case. The first column is the same. When T is 1, that means you can't have any elements in your matroid either. So that's highly trivial as well. When S is 2, then the element in E, they actually form a subspace. So E is just a subgeometry. So if you think about it, the second row corresponds to very highly trivial cases as well. So the first interesting case, I suppose, is when S is 3 and T is 2. But that case is also quite nice because you can show that if you're claw-free, so I3 or claw-free, or triangle-free, so we are excluding projected geometry in dimension 2, then you're actually an affine geometry, exactly an affine geometry. The proof is really nice. It's a sketch, but assume that your matroid is full rank just to make life a little easier. And I'm simply going to pick a basis of my ambient space, I suppose, G, and they're all contained in my ground set E. So I'm just taking a basis. And I'm going to think of them as unit vectors, so all support 1 vectors. And if I pick any 3 of them, so E1, E2, E3, then I can simply use triangle freeness to say that all these 3 points are non-elements, because otherwise you get a triangle. So for example, E1, E2, and E1 plus E2, that would be a triangle if E1 and E2 were an element of E. So that will give you a contradiction to triangle freeness. And by symmetry, you can say that the other 2 points are non-elements. Once you know that, then you also know that E1 plus E2 plus E3 has to be an element because of I3 freeness. You can just keep on doing this. So you can take any 3 elements, do this. Then you can, you have some information about all the support 3 vectors, but then you can use them and repeat the argument. And what you end up is that all the support vectors are in E and the even ones are not. So that means you're an affine geometry. It's one characterization of an affine geometry. So in this case, claw-free, triangle-free, you're an affine geometry. So in particular, chi is going to be 1 because there's a hyperplane that avoids the elements of your matroid. So this is also quite nice. So the answer is 1. So the blue cell is what we just proved. The next cell is a no because of the counter examples I talked about, the even plane matroids. The bad news is that if that's a no, then everything else here is a no because all of these classes of matroids will contain claw-free and final-free matroids as a subclass. So if that's a no, everything else is a no in that big blue region. So that's unfortunate, but that's how things are. So really the only interesting remaining cases are the ones that correspond to all these red cells. So all of this in the same paper. So they made this the following conjecture that for any given positive integer s, the IS3 and triangle-free matroids have bounded chi. So this is still open. The only thing we can do is that sort of Peter and I managed to show that chi is 2 when s is 4. So when you have I4 triangle-free matroids, then chi is at most 2. And it comes from a structure theorem. So you get this as a consequence of that. We don't really know how to extend it to say I5 triangle free or I6 triangle free. So they're very much open. But I'm not going to talk about the proof of this because there's I'm not sure how the proof is useful for the other cases. There's something else we managed to show whose proof may be more interesting. So I'm going to define a new matroid denoted I sub 1t for a positive integer t. So it's just going to be a matroid with a t-dimensional projected geometry as your ambient space. And E, your ground set, is just a single element. So it's this, for example, when t is t, so it's this large projected geometry dimension t, and you just have exactly one element in your ground set. So it's almost empty, but it's just got one element there. The reason we thought about this matroid is as follows. So this is the conjecture I wrote down a few slides ago. But if this conjecture is true, then certainly the I1T3 triangle-free matroids would also have to have bounded chi. So that would be a necessary condition. And the reason is that for any fixed S, or I suppose T in our case, so say T is 5, so I'm looking at I1, 5, 3 matroids, then I can find some large S, say 100, and an IS, I100 would contain a bunch of induced I15s, for example. So this is a necessary condition for this conjecture to be true. So we thought about it a little bit. Fortunately, it is true. So we can show that if you give me any t, then the I1T3 triangle-free matroids do have bounded chi, which is good news because we want the conjecture to be true. You might be wondering, why is this interesting at all? Because I gave you some motivation of why we considered it, but why? And one of the reasons I like this is that the proof may be a little more interesting than the statement itself. So I do want to go through the proof because maybe there's a chance that it extends to other cases. So the nice thing about thinking about simple binary matroids is that since you're essentially working within a vector space, you can use theorems from additive combinatorics. So the theorem we're going to use is a consequence of Green's regularity for abelian groups. So this follows from his theorem. And I'm not going to show why this is true, but I want to explain why this is useful. But just to make sure that we understand what the theorem is saying. So the theorem is saying that if you give me a dense set X, so that's the first condition, your set has to be dense, then this set X plus X plus X, which consists of all the points that can be written as X1 plus X2 plus X3, where X1, X2, X3 are all coming from X. This is a subset of F2 to the N. That's going to contain a large subspace or a large affine subspace. So an affine subspace is going to be a subspace minus a hyperplane. Right, so that's what this theorem is saying. This gives us a proof strategy. So what we end up doing in our proof is that we look for a set X which has the following two conditions. So the first condition we want is that we want X to be dense so that we can apply Green's regularity. Well, a consequence of Green's regularity. And we also want this set X plus X plus X to be disjoint from E. So we are looking for a set with these two conditions. And the reason is as follows. So suppose you have this and you just apply Green's, the consequence on Green's regularity. So the first outcome, the possible outcome is that you get a large subspace contained in X plus X plus X. So in this case, you have the following picture. So this large subspace, I'm going to denote by G prime. It's going to be disjoint from E, which is the ground set of this matroid. So it's a win because Green's regularity tells you that, well, G prime is large. So it's a win. So you get small critical number, which is nice. You could end up in this situation where you end up with a large affine subspace as opposed to just a subspace. In this case, what you have is this. So again, so G prime is this large area that you get from Green's regularity, but it's an affine subspace. So the shaded region in gray is all disjoint from E. And there's a hyperplane G double prime of G prime, which could contain, all sorts of points from E. But the point is, G prime is large, and this pink region will have to be I1 T minus 1 free. So that's the gain, and also triangle free. Now, why is it the case? If you had an induced I1 T minus 1, then I can make it a little larger by using this gray region and get an induced I1 T restriction, which is a contradiction. So you can induct on T. So that's the strategy. Any questions so far? Okay. So we actually need to find a set with these properties. So I'm going to start by fixing a point A and a hyperplane not containing A. So A and H. So that's what I've chosen so far. And I'm going to consider all possible triangles that go through the point A. There are three different types. You can get these triangles. So type A is a triangle going through A containing an additional point, an element from the matroid. And B is similar, it just behaves a little differently when you put it in the context of this hyperplane H. And the last point C, you don't have any additional points in that triangle. And you can't have a different type of triangle because of triangle freeness. You can't have a triangle containing A with two additional points because that's a triangle. So I'm going to color every single point in my hyperplane H, A, B, or C according to this rule. So it's very simple. The nice thing about this is that you can't have a large projected geometry consisting of just the B points, and you can't have a large projected geometry consisting of just the C points. In fact, in the case of the B points, two-dimensional subgeometry would suffice to get a contradiction. And the reason is as follows. So if you had a two-dimensional, or just a triangle, consisting of just the B points, then that's your left-hand side picture, and you already get a triangle lying in the hyperplane H. So that is a contradiction. if you had a t-1 dimensional flat consisting of just the C points, then if you remember what all the C points are doing, they're basically empty. So in this picture to your right, what you see is an induced I1 T restriction, which is a contradiction again. This is enough to say that the A points are dense. I'm sure there's a better way of saying this, but the way I saw it first was using geometric Ramsey. So by geometric Ramsey, there exists some constant R, a large constant R, so that if you have projected geometry of dimension R, and you color the points in B or C in any way you like, then you're going to get a two-dimensional subgeometry colored in B, or t-1 dimensional flat colored in C. So it's the geometric analog of Ramsey's theorem for graphs. And we saw that in these two cases, you get a contradiction. That's the previous slide. So you can't have a large projected geometry consisting of just the B or the C points. And by Bose-Burton, that means that the A points have to be dense. So this is nice. So you found yourself a set A. So I used X before, but I guess I'm using A, which are sort of dense. So it's looking good. So so here's a restatement of what we're trying to do. So the first one we have, the second one, the condition we want is that A plus A plus A. We want that to be disjoint from E. That may not be the case. So we are simply going to assume that that breaks down, and we'll try to see what we can do. So we'll be done if A plus A plus A is disjoint from E, so suppose not. What does that mean? Well, it means that you have to have something that looks like this. So you have X, Y, and Z all belonging to A, and their sum, the middle point, is in E. So that's what's making our strategy not work. So we're going to consider this matroid a little bit more in detail. So we can basically use triangle freeness to determine what this matroid is completely. So there are all sorts of points I haven't drawn yet, but the first type, if you will, so the points of the form x plus y or x plus z or y plus z. So there are 3 points of this type. I've drawn a red triangle in the ambient space, which goes through that point. So in this picture, y plus z. And the other 2 points are already in the matroid. So because of triangle freeness, this red dot, it can't be an element. So that's a non-element. By symmetry, I have the following. So all these 3 points, they're not in the matroid. I'm simply using triangle freeness. I can just do the same thing with the other points. So I could consider this point x plus z plus a, I suppose. I don't know if it's in the matroid yet, but there's that red triangle in the ambient space already containing 2 points from the matroid, the ground set E. So for the same reason, because we are triangle free, all these points are missing from the matroid. One final point, although we don't need it, is this point, a plus x plus y plus z. Again, there's a triangle in the ambient space going through that, which contains 2 points from the matroid already. So that's also going to be missing from the matroid. So this is the matroid we get. And if you look at it, it's just a 5 cycle. So it's a 4-dimensional matroid consisting of 5 points adding to 0. What we are going to do is quite simple. So since we got stuck we are going to replace this single point A, which we've chosen before, with this bad submetroid, which is a C5 in this case. We're going to repeat the argument. I'm not telling you how exactly that goes, but I'm going to take a flat disjoint from this C5. I'm going to color every point of that flat according to some rule. Some points will be dense, and we're going to repeat the argument. So in this case, here's my C5. I'm going to pick a hyperplane disjoint, not a hyperplane, a flat disjoint from this submetroid. And I'm going to color all these points in this flat according to how they behave with respect to this C5. And repeat the argument and see what happens. So that's sort of how the proof goes. Obviously, the question is, does it actually give us anything? Does it stop? The final point to make is that it does stop. And I can probably convince you of this by drawing this C5, which we've determined before. So there's a reason why I was trying my best to determine whether all these points were in the matroid or not. So there's this part of this matroid which I've indicated in blue, and that is an induced I3 restriction. So it so happens that every time you do this, you get a larger and larger I1 K restriction, and K is going up every time you do this. And since we are assuming that we are I1T free, this can't go on forever. That will complete the proof. So that's how the proof goes. So I'm sure that if you go home now and spend 20 minutes, you can recreate. You can obviously recreate all the arguments I made so far, and also fit in the details to prove our theorem that I1T and triangle-free matroids are chi-bounded. So I don't know what to do beyond this case, but maybe something like this could work to prove a more general cases of the geometric version of Java summoner, which I wrote down. Who knows? So that's the first theorem I wanted to talk about. I'm doing really well, so I might finish early. There's one more problem I wanted to talk about, which is the anextrumal problem, which I think Peter might have talked about this in December. So there's a question of ours which asks the following question. So what are the smallest IT3 matroids? I'm still talking about simple, well, actually, no, I'll come back to that point later. But what are the smallest IT3 matroids? The 2 points to make are, first of all, I need to consider full rank matroids, because otherwise I can just take the empty matroid, and that would be the best, which would be quite boring. So that's why I'm considering full rank matroids. And also the largest IT3 matroid would be just projective geometry. So the interesting question is, what are the smallest ones? There's a candidate. You can read this definition, but I think a picture would be much easier. So it's just going to be a bunch of projective geometry. So it's a direct sum of, so in this picture, 3 projective geometries. This is going to be I4 free, because you can't pick more than one element from each of these projective geometries. So the conjecture, our conjecture was that that's your extreme example. It is true. So Peter and Sergei Norin proved that that's the right answer. So the theorem statement doesn't include the equality statement, but it can also prove, in addition to this, that if you have equality, if and only if M is isomorphic to that particular matroid, provided the dimension is large enough, So when the dimension is small, you might have all sorts of different Matroid, but at some point, that's going to be your unique tight example. Actually, all of what I said about the extreme problem is valid for all simple Matroids, not just for binary Matroids. But I'm going to stick with simple binary Matroids during this talk. So here, I'm going to do a sketch proof, which I think Peter did as well. But it's going to be by induction on T. So I'm drawing this example on the right-hand side. So T is going to be 3. So I'm going to, what I want to show is what I want to determine is the smallest I4 triangle-free Matroids. So I'm going to assume that there's an induced I3 or claw, because otherwise you're done by induction. This is a very nice proof because what you end up doing, you just contract it. So you do M contract I, and you have to take the simplification. It's certainly the case that the simplification of the contraction is I4 free. Okay. But then when you took this simplification, you've deleted some elements. So I want to consider which elements you've deleted in getting the simplification. And if I take any point, so this red dot is this point I'm picking in M contract I, or the simplification of it, then it is certainly the case that if you sort of lift everything back to the original Matroid, that there was more than one point that you have to delete some element, because otherwise you get an induced I4. We are assuming we are I4 free in this picture. So every point in the contraction, the simplification, the contraction corresponds to 2 or potentially more elements in the original Matroid. So you get this relationship that the size of n, size of m is the size of E, but the size of m is going to be at least, so it's going to be greater than 2 times how many elements you get in the contraction. And the T is just coming from the first IT restriction I've chosen. So you can do induction on dimension now. And if you have this relationship, then you're done. What it doesn't give you is the tight examples, which are more difficult to determine, but it does give you the bound. So the simple idea is that you take a claw and you contract it and apply induction, and you get your answer. So one question they asked is the following. So since the tight examples are basically a bunch of projected geometries, which contain a bunch of triangles, lots of triangles containing them. So what if you impose the extra condition that you also have to be triangle free? So here's a question: what are the smallest, again, full rank, because otherwise it's going to be boring, IT free and triangle free Matroids? They have a candidate, and again, I think drawing the picture will be easier. So when T is 3, the Matroid defined here, it's just going to be a direct sum of 3 affine geometries. This is certainly going to be I7 free and triangle free. Now, triangle free is simple, and it's I7 free because you can't pick more than 2 from each of these blocks. If you take 3, then the sum of these 3 points will belong to the Matroid. So you can pick at the most 2, so it's definitely I7 free. And that was their guess. So when T is odd, so when T is even, you can ask the same question, but the extreme or the tight examples or the predicted ones aren't as nice, so I'm going to exclude them from this discussion. But when T is odd, then if you're IT free and triangle free, then you're basically you can't be smaller than this Matroid. Again, this is for general simple Matroids, not just for binary. And this conjecture is straightforward when T is 1 and T is 3. So when T is 1, again, it's highly trivial. You can't have anything in your ground set, so your Matroid is empty. when t is 3, that's the little theorem we proved at the beginning of this talk. If you're claw-free and triangle-free, then you're an affine geometry. So when t is 1 and t is 3, this is highly trivial. So the only, the first interesting case is when t is 5. And the extremal, the tight example predicted under this conjecture is the 2 affine geometries. So that's the first interesting case. At least for me, the difficulty about this conjecture is that you can't just keep on contracting things. So if you think back to what we did with just IT-free without triangle-free, then you pick some metroid, submetroid, you contract it and do some induction, and it just works. And one of the reasons why it works is that if you do contraction, well, then what you end up with is also going to be IT-free. In our case, if I do any type of contraction, chances are I'm going to lose triangle freeness. So that seems to be a difficulty. So the only known case is the case when t is 5. So that we managed to show. But there's a catch because we only did it for simple binary matroids. And really the idea comes down to, again, we basically contract a bunch of things, but the idea is that we are fine losing triangle freeness, but instead of sort of remaining I5 free, I want something more restrictive. What we end up getting is something that's, say, claw free, which is a more restricted class of matroids, something easier to work with. Okay, so the first step in our proof is actually to show that the tight examples are all affine. So that simply means that chi is 1. So if you look at the tight example, then it's an affine matroid. So the first step is to sort of to show that you have to be affine if you're as small as possible. I'm not going to show this step. It's actually quite nice and it's simple. But I think the next one, the next step is a bit more interesting. But suppose we have that. So we know that we are affine. Then what we're going to do is we're going to pick our largest affine geometry. And the reason is that, well, because that's our guess. The smallest example is predicted to be just 2 affine geometries. I'm just going to pick one of them. Uncontracted. And what we can show is that if you're affine and I5 free, I didn't say triangle free because that's implied by n being affine. So if you're affine and I5 free, and if you take a largest affine geometry and contract it and simplify it, what you get is something that's almost always claw free, not always. So there's one really annoying case when it doesn't work. But we can deal with it. So in almost all cases, you get something that's claw-free, which is nice. So we started with I5 free, and we went down to claw-free. That's not quite enough. And the reason is as follows. So say we have this large affine geometry, and I've contracted it. And what you see down there is the contraction. Now, if all I knew was that it was claw-free, then it could be the case that it's the smallest claw-free matroid you could possibly find, which is those 2 projected geometries. So if I told you nothing other than this information, it could be the case that you're left with that. Now, in taking the simplification, you've deleted a bunch of elements. So of course, one element in the contraction could correspond to a bunch of elements in the original matroid, but we don't really know much about that. And if you think about the size of the smallest I5 triangle-free matroid, which we're trying to get, it's basically 2 blobs. So you're removing hyperplanes and all that, but you need to get the size of basically 2 projected geometries. And if you look at this picture, what you're seeing is sort of 3 big blobs. And if you don't have further information, it will be quite difficult to say that the smallest example will be like 2 affine geometry or 2 blobs. So we need a bit more information. So here's my final slide. So what we end up doing is we consider a different another matroid, which is called 2T. And as the name suggests, it's just 2 triangles. So it's a 4-dimensional matroid and a direct sum of 2 triangles. So this is the matroid. What we can show is that if you take the contraction of a largest affine geometry, then it's going to be 2T3. And the nice thing about this is that it kills the extreme examples for claw-free matroids. So the smallest claw-free matroids are basically, given the dimension is large enough, is 2 projected geometries. But this actual condition of 2T3 kills that. And then you can show that if you're claw-free and 2T3, then you have enough elements for this argument to work. You have to work a little hard. Probably have to, I can't remember all the details, so probably have to do some argue a little bit about how each of these elements of the contraction, sort of how many elements that gives in the original matroid. But essentially, this is the argument. So it's interesting in the sense that I started with something that's I5 triangle 3, and I've reduced it to something that's I3 and 2T3. So I went down in terms of complexity when I'm talking about induced. The IT object, if you will. So I went down from I5 to I3, but then I sort of made my life a little more difficult by going from triangle 3 to 2T3. But it just so happens that I guess the gains are a little more than the loss, and we can show that, well, we can actually determine the smallest I3 2T3 matroids, and it works. The issue is that I don't know how to extend it to other cases. So when T is 7, so the conjecture says that you have to be a direct sum of 3 affine geometries. I don't know how to deal with that. So all these cases, except for the case when T is 5, are open, and as a matter of fact, as I said before, we only did it for simple binary matroids. But that's it. So thanks for listening.
Thank you. It's hard to do applause, but let me just say thank you again for speaking. I'm sure that there are lots of reactions in chat. So now let me open the floor for any questions for Kazu. Maybe I'll go ahead and get us started. You talked a lot about some positive results that you give whenever trying to extend these theorems for induced subgraphs and chromatic number to binary matroids. But like, there's so many different things you could try, I think, from that perspective. And it seems like a lot of them probably just wouldn't work. I'm wondering if you can talk more about like some negative examples. Like say it doesn't seem like something like the strong perfect graph theorem would even make sense to ask to me, for instance, but I haven't thought about it.
So I don't know. So the short answer is I haven't really thought about them. The long answer is that so the weak version of the strong the perfect graph theorem is actually true, but it's highly trivial if you put it in the context of simple binary matroid. I mean, the way I talked about them. So, for example, I think it's just a consequence of the even plane matroids having unbounded chi. But for example, claw-free matroids are not chi bounded, whereas they are for graphs. So for other cases, I really don't know. I mean, there's so many things you can think about. But now I don't have a good survey of what one can do here.
Thanks for the answer. All right, I'll go ahead and stop the recording. Thank you again.